Hi ladies and gentlemen, welcome to lesson 12. Today we're going to talk about null space and we're going to take a look at the extension of some of the ideas we were talking about with solving systems of equations. We're not quite to the point where we're going to solve all systems of equations. That's coming in the next couple of lessons. But right now we're going to talk about null space and we're going to talk about some of the things that Strang represents as ideas for how we're going to work through this. This is a complicated lesson because of the amount of stuff that we aren't covering that's in the textbook. Let me just run us over here for a second. And before we begin, I want to highlight an item that we talked about previously, but I want to make sure that you understand. So here's the syllabus, all the good material that you've read. And of course we have the homework section, we have the schedule that's provided here, and after the schedule, starting on page 5, we have course material, commentary, and text references. And this is basically the objectives of the course. This is the content from each section, from each lesson, if you will, that we are talking about. And we can see that there is a little bit for everything that we talk about, to include things like the supplemental section for vector spaces. What I want to do is point out the longest section that is in here, which is section 3.2. That's today. You need to make sure that you understand what this says. We're going to talk about several of the components in here, but you really need to make sure that you look through this. Obviously, you can look through every one of these and it's a benefit to you. But this one particularly, because of the amount of stuff that we aren't talking about and the emphasis on the things that we are talking about, which won't necessarily be perfectly clear in the video. So let's come back up here and take a look at the summary that Strang provides for us. So starting up here, what we're going to do is we're going to take a look at this first item. We're going to take a look at the null space. The null space is the set of solutions to ax equals 0. Obviously, 0 is a solution to that. And what I want to do is reference what we discussed previously, which is this graphic right here. This is my version, and we're going to see in a week or so a better version from Strang. This is kind of my version of what we're talking about. The point of emphasis that I want to make for you is the ax equals 0. Remember what that is, right? Ax equals 0, when we think about matrix vector multiplication, is a function. It's a mapping. And so we really are asking the question, what for this linear mapping, what inputs values give us a 0 for the output? And that's the null space. So the null space is this set of items which is mapping over to the 0 vector. And that's going to be our second big subspace conversation. The first significant subspace conversation we had is the range of this linear operator. It's the set of all possible outputs. And that is the column space of A. If you think about this, right, all we have here is linear combinations of the columns of A. And so all possible linear combinations of the columns of A, that's the column space, and that's one of our primary subspaces. So a big point of today's conversation is about yet another one of these important subspaces given some matrix A. But we want to think about that in terms of the matrix mapping. Okay, let's go back. We're going to take a look at this flow, which we highlight over and over again, and I just want to provide an introduction to what it is. So this is the flow where we are going from A to R0, and this is the process of RREF. So we are going to find the reduced row echelon form. We're going to use MATLAB to do this. We're not going to have any commentary about how we would do this mechanically because that's not something that we're going to focus on. And then the transition from R0 to R is removing 0 rows. So we're removing the 0 rows. And that's because the process of RREF will identify for us any redundant equations. So anything that's in the A matrix that is redundant, that information all gets zeroed out. And the resulting matrix R is exactly the same one as we saw when we did A equals C times R way back in chapter 1. those two things are the same. All right, so the next thing after understanding this flow, and we'll talk a lot about both of these matrices, for the most part, they provide us with the same information. All we've done with the R matrix is removed the 0 rows, that's all. So from an information standpoint, they are the same. So the next item that he talks about here is row echelon form, and this is exactly what we just said. So we have the reduced row echelon form, which is going to be the R0 matrix. But then he talks about this matrix F. And the whole conversation about the F matrix is what we're going to give it a little bit of lip service. We understand it's out there. We're not going to make use of it. That's why it has a niet symbol. So when you go and look at the syllabus and you look through the discussion for section 3.2 or any other section in the text, when you see a niet symbol, of course, that means it's material that we're not covering in depth in the course. Then the next one is this concept of special solutions. And I will show you multiple examples of what he means by special solutions. The next conversation here includes more of the F, and we aren't covering that, so we're not going to worry about that. And then finally, we have this comment. Every short wide matrix has non-zero values which solve AX equals 0. So it has a non-trivial null space. Let's take a look at that then. So he says, given a matrix of this shape, and we'll call this matrix A, then the null space of A is what we call non-trivial. And non-trivial just means that there's more than x equals 0. Right? So more than x equals 0. Because we know x equals 0 is always in the null space. There's no such thing as an empty null space. The 0 vector is always in the null space. If the null space contains only the 0 vector, we call it trivial. If it contains more vectors, which obviously is an infinite number of vectors, since we consider all possible linear combinations when we're talking about vector spaces, then that infinite number, we call that a non-trivial null space. So when it's short and wide, we have a non-trivial null space for A. Continuing on then, there's good conversation in here about the null space itself and kind of the matrices under consideration. Remember what's different with chapter 3 from chapter 2. We are considering matrices that look rectangular. We're not limiting ourselves to square matrices. So there's no reason for us to believe that M is equal to N. So this conversation's in here, and definitely you need to read through all of this. He calls this echelon form, and there's actually a distinction between row echelon form and reduced row echelon form, which we've touched on a little bit when we talked about Gaussian elimination. We'll touch on it a little more, but we're really only interested in reduced row echelon form. And then he starts out here with an example, and this is where I want to begin. What I've done is created a matrix here, and I'm going to show you in MATLAB how we calculate the RREF. So let me pull up MATLAB. And I've already input this A matrix, so here's the matrix here, which matches. And the command is just as simple as RREF. And the RREF command has many uses, and what we're looking at today is just the conversation associated with linearly independent columns, and really the whole idea of decomposing A into the C matrix times the R matrix, because that R matrix is the RREF matrix with the 0 rows removed. But then also the conversation about how we find the null space of a matrix. So let me throw this up. This is the RREF for A. And that's all there is to it. It matches exactly with what's in here. And he makes the comment in here that, hey, all we're doing, all the RREF is really doing is Gauss-Jordan elimination. That's what RREF is. It's executing Gauss-Jordan elimination. So let me just write this down quickly. So here we have the R matrix. If we think about A as the decomposition as C times R, remember the C matrix is a matrix that contains the linearly independent columns of A. So the C matrix, this is R, this is equal to R. The C matrix for the A, that's R, the C matrix would be equal to, and every pivot column, every column that contains a pivot, which are these leading ones that we talked about previously, those are the vectors, the columns that make up C. So in this case, it's the first and second columns of A. Those are, working left to right, the first linearly independent columns that we run into. So this would be C. So then if we took this C times R, then we end up having our matrix A. What I want to highlight here is the information that is in the R. We talked about this a little bit, but now we're really going to dig into this a little more deeply. What you'll notice is if we take the third column here and we sweep through the C matrix, which is how we would build the third column of A, you can see that we're going to have 3 copies of the first column, which is going to be a 3, 3, plus 4 copies of the second column, which is a negative 8, 8. So we have a 3, 3, and then we have a negative 8, 8. Adding those together, of course, is going to give us negative 5, 11. Similarly then, if we take 5, 6 and we multiply it, we sweep it through the C matrix, we're going to end up with 5, 5 plus negative 12, 12. And 5, 5 plus negative 12, 12 gives us our negative 7, 17 fourth column. So the point of this is the R matrix, the RREF, contains the information about how we use the linearly independent columns of A to build all the other columns. Now let's talk a little bit about null space. Let me write down the R matrix again. Because Gauss-Jordan elimination does not change the solution for a system of equations, solving AX equals 0 is the same problem as solving RX equals 0. So what we're looking for is, what is a vector here that we can multiply by that's going to give us the vector 0, 0 for an output? And there are 2 easy options. And this is what Strang is talking about when he says special solutions. And you can read about it, but I'm just going to demonstrate this because I think it's easier to see with a demonstration. What we're going to do is we're going to take one of the free variables. So we have the pivot columns and we have the non-pivot columns. And the free variables, when we're solving a system of equations like AX equals 0, the free variables are associated with the non-pivot columns. So x3 and x4 are our free variables. x1 and x2 are what we call fixed variables, or what Strang calls pivot variables. So what we're going to do is we're going to go in, and these are free variables, we get to choose them. So what we're going to do is we're going to systematically choose one of the free variables to be 1 and all the other free variables to be 0. So in this case, we're going to choose x3 to be 1, and then we're going to choose x4 to be 0. And the question is, if we make that choice, what values do the fixed variables have to be in order to give us a 0? Well, if we have 1 copy of the third column and no copies of the fourth column, to get a 0, we'll have to have negative 3 in the top here. So you can see when we push this through, we're going to have a negative 3 times 1, and then 0 times something, and then 3 times 1, and 5 times 0. And that's going to be equal to 0. So for the first row, we're satisfied. Now we need to move to the second row. What do we need to put in this spot in order to have the dot product of x with that second row be equal to 0? And the answer is negative 4. So this vector now is one of the vectors that's in the null space. And this is what Strang refers to as, he calls this the S1 vector, or the special solution vector. It's not special. It's just something that we build by being systematic with the free variables. Let's do the other example. And what I'm going to do is, now that we have this one up here, I'm going to change colors, and I'm going to provide the next one. So what is the next vector that if I multiplied, I would end up multiplying by A, I would get 0? Well, I'm going to pick x4 to be 1, and all the other free variables, of which there's only one, x3, I'm going to set that equal to 0. And now what do I have? And now you can start to see the pattern. I'm going to have, if I have a 5, I'm going to have a negative 5 here. And then I have in the second row a 6, and I'm going to need a negative 6 here. And this is what Strang calls S2. And so what he has found are two vectors that are in the null space, and he goes on to show us that these vectors actually span the null space. This is a basis for the null space. So the null space of the matrix A that we started with is the span of S1 and S2. And that's where he's headed, and that's his comment right here. Right? The special solutions are a basis for the null space. Let's do another example. Let's take a look at example number 2 here. And again, I've just come up with a matrix that is going to give me this as the RREF. There are an infinite number of matrices, right? If you think about this RREF right here, and let me just write it down. So we'll take a look at this RREF matrix, and we can see exactly what the C is going to be. So this is R, and in order for us to make A equals CR, and I apologize, I called this C. I'm talking about something different with the C for CR. I'm looking at the linearly independent columns, which are the pivot columns in C. So it's this first column and this column here. As we discussed, R tells me how the rest of this matrix has been built. So what I'm going to do is, right now I'm going to make a game time change. I'm just going to change this to the A matrix to avoid confusion. So it's the matrix A, and we can see that the second column is 7 times the first, and sure enough, that's exactly what we have. And we can see that the fourth column is 8 times the first column plus 9 times the second column. And that's what we have here. So that information is what's provided in the RREF. Again, many uses for the RREF. This is one of them. It's also an avenue, and let me be perfectly clear with Strang's notation. He calls this R0. And so what he would call R would be equal to removing the 0 rows, 1708 and 0019. That would be the R. And then the CR combination, I would have to get the two linearly independent columns, which are 3, 0, negative 2, and 1, 1, 1. And then this is our CR matrix. And that's what A is equal to. Exactly what we talked about back in section 1.4. So from this, we can find the null space. We want to take a look at solving AX equals 0, but we know that that's the same as solving R naught X equals 0, which is the same as solving RX equals 0. The solutions for any one of these is the same, because Gauss-Jordan row operations do not change the solutions. So what we want to do then is we just want to take a look at 1708, 0019. What do we need for something that we can multiply by that gives us the 0 vector? We're going to do exactly what Strang recommends. It's the best approach. We are going to take the free variables, which in this case are, the free variables are x2 and x4, because those are the non-pivot columns. And we're going to set one of them equal to 1 and all the remaining equal to 0. So we're going to set 2 equal to 1, and then we're going to set x4 equal to 0. And now we're going to calculate what is required for us to be able to get a 0 when we do this matrix vector product. And the answer is quite simple. The 1's going to give me a 7, so this is going to have to be a negative 7. And then this one down here, I'll put in a 1, 0, I don't know. We have to check it against both vectors. I need both to be 0. So it turns out I need a 0 here because my x3 is a fixed variable. And because I've set x4 equal to 0, it turns out I need to set x3 equal to 0. So this is S1. Shifting over to our green color again then, what's another vector? Well, I'm going to make x2 0 and I'm going to make x4 1. So when x2 is 0 and x4 is 1, the top equation is going to require a negative 8 up here. With the negative 8, I'm going to be able to get a 0. For the second row, or the second equation, I'm going to need a negative 9. And now I have a vector that when I do the dot product with the first and second rows of the R matrix, I end up with 0, 0. And if you're not convinced, you can verify that for yourself. This is S2. And just as he said previously, the null space is the span of S1 and S2. So from the RREF, this is an easy way for us to find out what a basis is for the null space. He talks about the free variables here. He talks about the equations, and this is, if you're having trouble understanding the matrix vector product that we're talking about over here, you definitely want to spend time writing out this material and understanding exactly what he says, because ultimately, as always, the rows are equations. So this first one says x1 plus 7x2 plus 8x4 equals 0. And the second equation says x3 plus 9x4 equals 0. And we have to solve those simultaneously to come up with solutions. And of course, the easy way to do it is to set x2 equal to 1 and x4 equal to 0, and then vice versa. x2 equal to 0 and x4 equal to 1. All of that is what he's talking about in here. So he talks about the plan for the book, talks about removing all of the 0 rows, and then he gets into his conversation about F. And so let me just briefly touch upon, because this is a big part of what he's talking about, and it's not incorrect at all. He's emphasizing how we can use the matrix ideas instead of just going through and coming up with these solutions in this manner. He's talking about how we can do this. Well, when we have a really easy problem, like this one here, it's very easy to see that we have the identity matrix and we have his F matrix. That doesn't come up very often. Oftentimes, we end up with an RREF where the pivot columns are mixed throughout, not just all stacked at the beginning of the RREF. And that's where he's talking about this. Well, here the I is buried in the first and third columns, and the F is in the, let me change to a darker color, the F is in the second and fourth columns. And so what he tells us is, hey, we're going to need to apply a permutation matrix in order to get the I and the F to look the way we want them to look. All right, there's no need for us to do that. That's a great and interesting matrix manipulation idea, but we don't need to do that. What we need to be able to do is this. We need to be able to find a basis for the null space and understand what that is. Continuing on then, he talks about elimination from A to RREF-A. And we're not going to go through the details of this because we are using MATLAB's RREF command. He does walk through how it gets done. What I want you to emphasize, and make sure you understand is these steps here are the Gaussian elimination steps we talked before. We're doing nothing but Gauss-Jordan elimination, right? So the RREF is the same as doing Gauss-Jordan elimination. And with that, of course, we take those pivots and we turn them into leading ones. That's something that's always done when we calculate RREF. So this whole section gets into yet. We're not talking about the W matrices and the H matrices. This all has to do with the matrix manipulation that he's talking about. So this, however, is important information. The first R independent columns of A locate the columns of R containing the identity matrix, because those identity matrix columns, if you will, those are the pivot columns, and those pivot columns in R, those match up with the set of linearly independent columns in A. Then he says the remaining ones, the non-pivot columns, those are the columns that make up his F. So both of those things are true, and they're integral to what he's talking about with the matrix manipulation. What we need to understand is pivot columns, non-pivot columns. Pivot columns give us our linearly independent set of columns, which are the columns that go into C. So remember, this whole thing is kind of based on A equals CR, because this is the RREF with the 0 columns removed. And so the pivot columns tell us, right, this thing here. So this comes from the pivot columns. It's important to realize, though, that they aren't, the C is not the pivot columns. C is the columns in A, which line up with the pivot columns. And he provides us with another example. You'll notice that his A matrix here is completely different than the one I selected, and it comes up with the same RREF. So we can't back engineer from the RREF what the original matrix was. We need the set of linearly independent columns to do that. So in his case, his linearly independent columns are 1, 2, 2, and 3, 6, 9. Those are the columns that we have to deal with. The next section here, this is when you look through the material in the syllabus, you'll see that we are not covering any of this. We are using the RREF command in MATLAB. So I don't want you confused by this algorithm at all. We'll look at our own algorithm when it comes to that time. So don't worry about this. And now what we want to do is we want to look at the matrix factorization and the null space. And this is really kind of a review of what we just discussed. And you can see he walks through the same second example that we went through, and he talks about how he finds these vectors, which are the same ones obviously that we found, and it's all based upon his approach of the special solutions, where he makes the free variables into 1, 0, and 0, 1, and then he calculates the other two variables. He talks about how that relates back to his F matrix. We're not talking about that. Same thing here, we're not having this discussion. So a couple of examples, and then we'll be close to understanding what's happening. And really, this is like everything else that you're learning in mathematics. It's a game of repetition, right? You do this several times and it will become second nature. It's not that it's an intellectually complicated idea. So here he gives us a matrix and he executes the Gauss-Jordan elimination and comes up with this thing here as the RREF. And then, of course, he pulls out this as his R matrix because he's just removed the 0. So first things first, let's use this example, and we're going to have A is equal to CR. And that's equal to, we're going to have some C matrix. And then the R matrix has already been given to us. I'll just write it down, 1, 2, 0, 0, 0, 1. We can tell from the R matrix that we have a set of two linearly independent columns, and those are the first and third columns of A. So the first and third columns of A are 1, 2, 3, and 1, 5, 9. Moreover, the information that's in R tells us how we would build that second column. Right, so let me highlight this. This piece of information tells us how to build the second column of A. And we just take that 2, 0 and we sweep through the linearly independent columns and we see it's twice the first column. And that's exactly what we end up with when we look over here. That second column of A is twice the first column. So there's a lot of good information in here. There's good rank information in here, right? So the number of linearly independent columns is the rank of the matrix. So we know that the rank of A is equal to 2, and he has that conversation. And of course, we understand that column rank and row rank are the same, so they're both 2. And then there's the question, well, is there a null space? And the answer is yes, there is a null space, and we know there's a null space because we have free variables. Free variables are our connection to the null space. So let me just write down the R again. We have 1, 2, 0. And 0, 0, 1. And the question is, what's in the null space? Well, we start with free variables. In this case, we only have one free variable. So we're just going to set that free variable equal to 1 and figure out what we need. Okay? So when we set that equal to 1, we can see that the first entry in our null space vector is going to have to be -2. And then in order to solve the last equation, we can see that this is going to have to be 0. And when we do this matrix vector multiply, of course, we get the 0 vector. And this is what Strang would call special solution number 1. In a lot of textbooks, you'll see this written as N1 vector for null space vector number 1. And then we understand that the null space, and let me just be complete in this one, so the null space of A is equal to the span of the basis. And in this case, the basis is the vector -2, 1, 0. Right? And this is our null space. While we're practicing, let's talk about column space. What's the column space of A? The column space of A is the span of the set of linearly independent vectors, which would be the vectors that are in the columns that are in the matrix C. So it's 1, 2, 3, and 1, 5, 9. These are the columns of A, which form a linearly independent set. That's the column space. Let's review a little bit more. We know that A is 3 by 3. So because A is 3 by 3, A is mapping R3 to R3. And we know what the null space is, and we know where it is. The null space is over on this side. So let me change colors. I'll go to the cyan here. The null space is over here because it's all the stuff that maps to the 0 vector. The column space is over on the other side. So the column space is over on this side. It's all of the vectors that can be built as a linear combination of the columns of A. We'll talk more about this. This is coming up in a few lessons. So he does the same thing here. He goes through this. I wanted to provide you with that example. And then down here, we have a good example, and you should work through all of this. So make sure that you're reading through. Obviously, you need to read through the sections as we go, right? The videos are not sufficient. Read through this. The videos are here to help you understand some of the nuances. You don't need to worry about the F. If you're interested, you can look at how he's built this F, but that's not part of what we're talking about. However, you do have to understand this whole concept of how we find the null spaces, how we use the RREF. What I want to do is I want to provide you with just one more example down here. Here's a reshape command. You can do that on your own time if you want. This is one more example. And this example is so straightforward, we don't need to use MATLAB to figure it out. So what is R0? What is the RREF for this? Well, what we see is, just look at the columns. We have a 1, -2, -1, and then a -2, 4, 2, and a 4, -8, -4, and a 1, 2, -1. And so what we see is we have the first column is of course linearly independent because there's nothing else it could be dependent with. The next column is -2 times the first column. So this gets a 1. This gets a -2. This gets a 4 because the third column is 4 times the first column. And then the last column is linearly independent from all of the previous columns. So that gets something that looks like this. And that's our RREF. And we can see from that that we have 2 free variables, x2 and x3. And now you know how to use those free variables in order to find the special solutions and ultimately find the null space as the span of those special solutions, that basis. That's it. All right, so this happens on occasion. I forgot to throw up the questions for the participation questions. So these are the questions we have. Execute the RREF and then go find the special solutions and then come up with some matrices. Be a little bit creative with the ideas here, and it will help you to understand what's happening. Remember a lot of concepts that we're emphasizing. All right, thanks very much.